In this lecture, we're going to be talking about a different type of wave, and these are known as tides. So I have this first picture here to introduce tides because many of you may be familiar with this process already and know that depending on what time of the day you'd like to visit the beach, the water level could be more or less encroaching upon the shoreline. So this person here parked their car obviously during something called the low tide and abandoned it for a couple of hours, not realizing that there was a huge difference between the water level during high and low tide. And so you can see that their car has been completely encompassed by that. So today we're going to be talking about how tides are something that we say is rhythmic. And you can think of that like a heartbeat. So it's regular rise and fall of sea level. Tides are very long and shallow water waves, which are caused by the gravitational attraction between the sun, moon, and earth. So as we're going to see in this lecture, our oceans are under the influence of the moon and the sun's gravity. So anything that has mass in our universe exerts a gravitational attraction on other masses. So because the moon is so large and so close to our planet, it pulls our oceans away from us. And so because of that, different tidal patterns exist, and we can define each of those based on their occurrence. So tides are something that occurs daily, and they're caused by the combination of gravity between Earth, the moon, and the sun. Isaac Newton's gravitational laws explain this relationship. So one of Newton's laws is force is equal to mass times acceleration. So anything that has a mass is going to exert a force on something else. This demonstrates something called the barycenter between moon and Earth. So two objects of two different masses will have something called a common center of mass, or a balance point. So in the moon-Earth system, that barycenter is not actually the center of the Earth, it's offset here. And that's because the moon does have a significant mass, although it's not as big as Earth. It's enough to pull that barycenter away from the middle point of the Earth. And so you can see that demonstrated here, where we have this scientist swinging this round metal ball, right? So this ball is traveling along a straight path, but because it's tethered, in this case we're looking at gravity, it's tethered by gravity and makes a circular orbit. So because we have Newton's law, force equals mass times acceleration, that means that every particle attracts every other particle. And the two important things to remember about that is, one, it depends on the mass of the object, and two, it also depends on the distance between those two objects. So, for example, the Earth doesn't collide with the sun, even though the sun is exerting a gravitational attraction on Earth. The sun is so far away from our planet that that force is negligible. So when we look at the force exerted by gravity, we have to consider distance. So here you can see this mass is one force. Two of those masses would be 2, 5 would be 5. So that's the effect of mass on gravitational attraction. If you increase the mass, you increase the force. And that's inversely proportional to the square of the separation distance. So you can see here, the separation distance is labeled R. Right? So this is displaying the effect of distance on that gravitational attraction. At this picture here, the spaceman is located much closer to Earth. Right? R is about 1/2 of this. So that spaceman is going to feel a larger pull towards the planet simply because they are closer to it. Whereas this, space woman out here, she won't feel that pull. She won't be sucked in towards the planet because she's far enough away that won't be an issue. So those are two very important things to consider when we're looking at the gravitational force. So a few vocabulary words. Where Earth sees the greatest gravitational force is known as something called the zenith. So that would be the point that is at the closest distance to the moon, because remember, distance is important. The further away you are, the less of a force you'll see. So the minimum force or the least force is at the nadir. So furthest from the moon and opposite the zenith. So that would be here on the other side of Earth. You can see the arrows here. These are called vectors. So a vector in science displays two pieces of information. The first is it gives you a direction. So what direction is the arrow pointing? That tells you the direction of the force. But also you want to look at the length of the arrow. So the longer the arrow, the greater the magnitude. So for example, that force is greatest here, and you can see the arrow is the longest of all the arrows. Whereas at the nadir, where you have the least force, that arrow is the shortest. So the vectors give you those two pieces of information. What direction is it being pulled towards, or the force, and also how much, how long is that arrow. So we can see here, every point on Earth, that arrow will look a little different. Right, so it'll be shorter the further away it is from the moon's center of mass here. And they're all going to be pointing towards that same center of mass, which means these arrows here won't be parallel because they have to be oriented along this line to the moon's center of mass. The second type of force that is associated with Earth's tides is known as the centripetal force. And this is also known as a center-seeking force or a rotational force. And this is actually what tethers the Earth and the moon to each other. So you can think of centripetal force like you would a roller coaster. It's why you don't fall out of the roller coaster when you go upside down. It's the same reason why if you put water in a bucket and you swang that bucket over your head in a circular motion, the water doesn't fall out and splash you in the face. That's because of the centripetal force. It's a center-seeking force associated with rotational movement. And so we know the Earth has rotational movement. It makes one rotation in 24 hours. But regardless of where you are on the planet, these vectors will be parallel because Earth only rotates in one direction. So each of these arrows will be parallel to that rotation direction. So you can see they're all pointing towards the moon, right? And they're also all the same length because that rotation does not depend on gravity. It's purely a result of that centripetal motion. So then what we can do in math and in science is we can calculate, okay, well, what will be the resultant force, or the force that is the result of if we add both the gravitational attraction, which was this picture here, and we add those forces to the centripetal force from this picture here. So you can see that represented by the red and black arrows. They've just been duplicated onto here. So if we want to figure out how that will affect the tides, we have to do something called a vector addition. So we basically add these two arrows together, and the result is the blue arrow. So how you make a vector addition is by linking the tail of one of the arrows to the point of the other, and then the gap is the resultant vector. So the blue arrows indicate what the tides will do. It's the combination of both gravity and the centripetal force. So that's a very important point because on your test, I'm going to ask you what causes the tides. And it's not just gravity, it's also the centripetal force. Right? So it's due to both of these things combined. So you can see that leads to a blue arrow pointing outward on this side of the planet, and then on the other side of the planet you have this blue arrow pointing outward. Whereas at the north and south poles here, for example, you have the arrows pointing inward. So what this means in a nutshell is that where you have arrows pointing out, you have a high tide. Where you have arrows pointing in, you have a low tide. And where you have arrows that are pointing outward at an angle, you're having somewhere in between high and low tide. So this leads to this picture here. The resultant force has significant horizontal components, and so it pushes Earth's oceans, its water, into two bulges. So those are called tidal bulges, and that's one of your questions. So one bulge is towards the moon, right? So you saw that here, that blue arrow towards the moon, and then the other is away from the moon, which is this arrow here. So those are the two tidal bulges, and you only generate those because of both the combination between gravity and the centripetal force. So you can see here the blue arrows indicate the maximum tide generating force. So that picture illustrates the tidal bulges, right? So we have one on this side and one away from the moon and one towards the moon. So at any time there will be a tidal bulge on both sides. So our oceans bulge away towards the moon. The moon is physically pulling this water away from its planet, but obviously the moon is not strong enough to pull it away entirely. So that's why we have the tides. So at each tidal bulge, you have a high tide. And then here, where you have no tidal bulge, you would have a low tide. So Earth itself rotates once every 24 hours. And during that 24 hours, it will rotate through two different tidal bulges, right? So that means that every day you will have two high tides and two low tides with one rotation of Earth. So some tidal phenomenon. The tidal period, that's the time between two high tides. And when we define some of this vocabulary, it's important to distinguish the difference between the Earth day and the lunar day. So the lunar day is different. This is the time between two successive overhead moons, which is about 24 hours and 50 minutes. Whereas we know that Earth Day is only 24 hours. So because of this, and this is a question on your test, is because of the difference between the Earth Day and the lunar day, high tide will be at a different time every day. So that's why you have to go and consult the tide charts to make sure that you go to the beach. If you're going for a hike along a rocky area, you want to be careful that you don't accidentally strand yourself while coming back and high tide rises. So high tides are 12 hours and 25 minutes apart, so half of this value here. So you can see that demonstrated really well in this picture. Here we have the North Pole, the lunar tidal bulges. Here's your reference point after 6 hours, after 12 hours, 18 hours, 24 hours, and then finally at the end of the lunar day, 24 hours and 50 minutes. So up until this point, we've only discussed the effects associated with the gravity of the moon. But it's important to know that the sun, because it's so massive, right, because of its sheer size, even though it's so far away from Earth, because of its size, it does influence the tides to a certain degree, albeit it's not as much as the moon. So if you see a question on your test that says what contributes the most towards Earth's tides, that is the moon. But the sun also does influence them to a small degree. So here are some vocabulary words for you to understand that have to do with Earth's rotation and tides. So here we can see we have a tide chart. Right? Maybe you guys have seen one of these before, and it tells you the time that you're going to have your high tide and your low tide, and everywhere in between will be segmenting between the two. So a flood tide, which you can see here, this is where water is moving towards the shore. Whereas an ebb tide is where you have water moving away from the shore here. Tidal bulges, remember, they're fixed relative to the sun and moon's positions. So Earth's rotation moves different geographical locations into those tidal bulges. The incoming tide along the coast and into the bays is called a flood current. The outgoing tide is called an ebb current. The strongest flood and ebb currents usually occur before or near the time of high and low tides. However, in the open ocean, it's important to know that tidal currents are relatively weak. So now we can take a look here at the Earth, Moon, and Sun's positions relative to something called spring and neap tides. So here you can see we have a full moon, our new moon. This bulge represents the lunar tide, and then we also have this smaller tidal bulge here, which is the bulge due to the solar tide. And you can see that this will change depending on the phase of the moon. So now we're looking at a first quarter moon and a third quarter moon. The bulge will be towards the moon. This lunar bulge will always be towards the moon, but the solar bulge, you can see here, is pointing towards the sun. So the result is that during spring tides, during new moon or full moon, your tidal range will be the greatest because you're adding both the lunar and solar tide on top of each other. So at those points, you'd have more significant tides. Whereas neap tides occur during the quarter moons, right? So the tidal range will be the least because you have these two spread out, somewhat equally around the world. Albeit the lunar tide is a little stronger here, but they're not both being combined together, so we call that the neap tide. It's where you have the least tidal range. Okay, so those pictures I showed you before, these are the ideal pictures that we show to get an understanding of how tides work, how the tidal bulges are generated. So now that you have that understanding under your belt, we can talk about some of the non-ideal factors. So one of those we know is declination. So that's the angular distance of the moon or sun above or below Earth's equator. So in those previous pictures, remember, we had the tidal bulges oriented perfectly around the equator. And that's great for teaching concepts, but remember, because of this angular distance of 28.5 degrees to the moon, the tidal bulges will be oriented as you see here. The sun to Earth is 23.5 degrees north or south of the equator. So lunar and solar bulges shift from the equator, and that contributes towards unequal tides. So we can use all of this information, right, when we look at predicting idealized tides. This is something that we can do very well because we know the mass of the moon, we know the mass of the sun, we know the speed of Earth's rotation, we know the period between successive new moons and quarter moons. So we can calculate with high precision at certain times of the year or certain times of the month where high tides and low tides will occur, whether they will be a high tide or a low high tide or a low tide. So you can see here, this shows that person moving in and out of the tidal bulges with one rotation. So they're going to witness 2 high tides and 2 low tides in one rotation in 24 hours here. So this is called a tide chart, right? So you can see, depending on your latitude, that's going to matter. So first you need to know the location of where this person is. And you also need to know the time, right? And that will tell you the water level. So here you can see A is a high tide, whereas C is also a high tide, but it's not as high as this one, right? So looking at tidal charts can give you an idea of where the water level will be at any time of the year, at any day, based on those physical constants that we discussed. So some other complicating factors include the fact that objects in our solar system don't make perfect circular orbits. They make elliptical orbits, more like an ellipse. So, for example, looking at Earth's trip around the sun, the tidal range will be greatest at something called the perihelion, which is in January. where Earth is closest to the sun. Whereas the tidal range will be least at aphelion in July. So that's where Earth is going to be furthest away from the sun in its elliptical orbit. For the moon around Earth, tidal range will be greatest at something called the perigee. So moon is closest to Earth, and tidal range will be least at the apogee, where moon is furthest away from Earth. So that whole perigee, apogee lunar cycle is roughly 27.5 days. So here you can see that demonstrated. So the orbit of the moon around Earth is not a perfect circle, and the movement of Earth around the sun is also not a perfect circle. So because of that, at some times of the year, in January, Earth is at its perihelion, it's closest to the sun, and tidal range will be greatest. Whereas in July, it's further away from the sun, and so the tidal range will be smaller. So the same goes with the moon and its rotation around Earth as well. So when we look at idealized tide predictions, we know that there will be 2 high tides and 2 low tides per lunar day. And there's 6 lunar hours between successive high and low tides. So this is a good picture here if you're studying for our final and you need to get an idea of how this tidal bulge relates to our tides on Earth, is that, remember, Earth is rotating beneath our oceans, right? Beneath these 2 tidal bulges. And that can be kind of a weird concept to wrap your head around. So for example, I have shown here, this is a tidal chart, and it's linked to the corresponding location in the moon cycle, right? So you can see you have a new moon here, a full moon here. So depending where the moon is in its orbit around Earth will determine the tidal range. So you can see some weeks have very high highs and very low lows, whereas other weeks that high and low is more close together. So that's the combination of all of those different elements between the moon's rotation, the sun's rotation. You can see that you're going to have this chart, but it will evolve in the same way because Earth's orbit around the sun doesn't change, its rotation doesn't change. So that's why scientists can use these charts with high precision and accuracy to determine what places, what geographic areas at what time will see what change in regional water level. Okay, so it's a little bit of a short lecture, but you do have an accompanying 5-point quiz to go along with that. And I will see you guys for our next lecture.